Alright, so here's a problem on the Riemann-Stieltjes integral. And for this problem, we are given that f is a bounded function, alpha 1 and alpha 2 are monotonically increasing functions. We want to show that if f is Riemann integral with respect to alpha 1 and with respect to alpha 2, then it's integrable with respect to alpha 1 plus alpha 2. And the key here, key theorem, is that f is Riemann integrable with respect to alpha on a, b, if and only if for all arbitrary epsilon greater than 0, there exists partition P. And remember, our partition is just, like 0 equals a, x2, x2, what am I saying? x1, x2, blah, 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 xn equals b, where x0 is less than or equal to x1 is less than or equal to x2, less than or equal to xn, such that, and this is key, u of p comma f comma a minus l of p comma f comma a is less than epsilon. And remember that this is basically our partition of, so this is mi delta a I minus ni equals 1 mi delta a I, where this is the supremum f of x, where xi minus 1 is less than or equal to x. So in other words, x is in the interval xi minus 1, xi. Similarly, this is the inf of f of x, where x is on the interval, on the closed interval xi minus 1, xi. And this is just alpha of xi minus alpha of xi minus 1. All right, so with those definitions out of the way, let's tackle this problem. First, we're just going to write out what exactly are the upper and lower sums of f with respect to this. So the upper sum of p f a1 plus a2 is just going to be equal to I equals 1 to n of mi delta a1 plus a2. All right, and this will just simplify to be, because of just how sums distribute, that's going to be equal to mi delta a1 plus ni equals 1 mi delta a2. Okay, actually this should be I. All right, now we are going to do the lower sum, and that is going to be very similar. Blah blah equals ni equals 1 I delta a1 I plus equals 1 mi, this is the infimum 2 comma I. All right, so since we know that, okay, actually yes, so let's just try to see if the criterion is true. That is, does there exist partition such that the upper sum minus the lower sum is less than epsilon? Well, let's just subtract them. So u of p comma f comma 1 plus alpha 2 minus the lower sum, that's just going to equal ni equals 1 mi delta a1 I plus ni equals 1 I delta a2 I minus n I equals 1 mi delta a1I minus n I equals 1 mi to a2I. All right, and from here we can actually see something pretty convenient, which is that when we subtract this mi, okay, let's try that again. So when we subtract these two, that's actually just going, there actually will exist a partition such that when we subtract these, that will be less than epsilon over 2. And why that is because f is Riemann integrable with respect to u1. So there exists partition P, partition P1 such that n I equals 1 mi 1I minus I equals 1 mi delta a1 I is less than epsilon over 2. And similarly, when we look at this, subtract them, there exists P2 such that this with respect to alpha 2 I is less than epsilon over 2. Okay, and from this fact, we can see that this will actually be less than epsilon for, this is really important, the refinement partition P1U P2 equals P. And why that is because given an epsilon for which this is less than epsilon, for any refinement of it, that is for any P1, P with like the points of P1 and more points, that will be even closer. So these will be even closer to each other, to the supreme and infimum, because the intervals are getting smaller. So it'll be definitely less than epsilon over 2 for this refinement. And because this shared partition works, so this partition will actually work for alpha 1 and alpha 2, we know that there does exist a partition for which the upper sum minus the lower sum of f with respect to alpha 1 plus alpha 2 is less than epsilon. And we're done.